In this video we will see very important topic in probability and random processes. The name of the topic or the name of the point is random process. So there can be a chapter on random process, or then it can be a subtopic in any of the topic under probability and random processes subject. So let us define what is random process, what is the definition of random process. So it is very difficult to understand if you read the thing through the book. So let us simplify it and try to understand it, what is random process. Dear friends, many physical phenomenon in nature, they are best characterized in terms of statistics, because almost all phenomenon in nature, they are random in nature. So in general, all these phenomenon, whenever you are trying to analyze, whenever you are trying to interpret, whenever you want to extract something through this phenomena, there is a need of statistics. So many physical phenomenon in nature can be well represented by its statistics. So many physical phenomena occur in the nature can be best characterized by its statistics, or can be best characterized in terms of statistics. Now if we want to understand this random process, so let us consider the example. The example is from meteorological phenomenon. Meteorological phenomena, under this phenomenon, air temperature and air pressure fluctuation. If we consider air temperature or air pressure fluctuation in different cities around the world, and you plot the graphs of air temperature versus time in different cities around the world, whatever maximum possible. The set of or each city corresponds to one sample function or one single realization. There will be one waveform for temperature with respect to time. Let us say we have collected the temperature for the period of 4 hours, 6 hours, something like that. So one city corresponding to one realization or one sample function. So if I consider different cities around the world, you will be having different realizations or different sample functions. Collection of all these sample functions with respect to time, that is called ensemble function or ensemble with respect to time. So here whatever we took whatever we have taken pressures, we have taken time, temperature or pressures. If we take all those temperatures or pressures with respect to time, if I consider pressure with respect to time, so all together all pressure waveforms with respect to time, or if we consider temperature, all temperature waveform with respect to time. So collection of all these waveforms is called ensemble, and that ensemble, which is function of time, set of collection of all these sample functions or realizations is called ensemble, or we can say it is a random process. Many times in electronics, when we come across electronic devices, if you measure the voltages across all registers present in the device, and plot all these waveforms for one waveform for one register. So there are so many registers, plot their waveforms, and that collection of waveforms is called random process. So maybe if you consider transmitter or receiver having so many registers, across each register you measure the voltage over the period of time. For single voltage we get single waveform, number of voltage and for single register we get single waveform. If there are number of registers in the system, so you get number of waveforms, and all these waveforms taken together, collected together, one above the other, then that becomes random process. So collection of all time profiles of different cities, this is one example, or collection of all voltages across all registers present in the electronic devices, especially transmitter, receiver, and kept one above the other, that becomes the random process. That is the random process. So in case of this random process, if you are trying to see in pictorial form, so how it looks, that we'll see for example of air temperature with respect to time. So I am just going to plot the picture of a random process. Okay, let us see the picture of random process. And here one more point I forgot to tell you, all such signals means random processes, they are considered to be infinite duration, infinite energy signals. Infinite duration, infinite energy signals, very important thing. Infinite duration and infinite energy signals. So we have seen, I am telling you meteorological phenomenon, that is air temperature or air pressure across all cities in the world, or thermal noise voltages generated in the registers of electronic devices. Collect all waveforms across each register, put together, that becomes the random process. Before drawing the diagram, let us see whatever we have spoken. To represent the random process in terms of notations, let us see that the set of possible waveforms of random process is denoted by XTS. It is entire random process, okay, all sample functions, all time instants t. So random process is denoted by X of Ts, where t represent the time index and s represent the set of all possible sample functions. So X of Ts is a notation which we will be using for the random process. So, and for single realization of this X of Ts is denoted by small x of t comma s. A single realization or single waveform is denoted by XTS. The set of all possible waveforms of a random process is denoted by XTS. So this is the notation for random process. Require two variables. T represent the time index and S represent the set of all possible waveforms, and whenever I am calling single waveforms, so it is x of small x of Ts. Mathematically, again, if you want to define or represent or explain the random process, it is simply we can say that it is a mapping from sample space to real line. Sample space, no, it is a mapping from S cross R to R. X is a random process. X is a random process which requires sample space, which require time instant for its definition. So a random process, if we actually try to define mathematically, So it is a mapping from S cross R to R, S cross R to R. So this outcome of the random process, that is always real. So anything, one realization from here and time sequence from here gives single realization, right? So outcome of experiment, or if I consider the temperature of one particular city, right, I am having collection of temperatures, okay, here all time instants, so temperature and corresponding time instant, so I am mapping to a real value, right? So random process, I can say process is a mapping from sample space, mapping from sample space, or we can say that from, this is a sample space, S cross R. Here I am taking sample space as well as time instant into account, to R, resultant is R, that is important. So if you try to plot random process, so let us plot it. So this is time axis, these are the, let us say, one sample function, for line for one sample function, line for another sample function, and dot 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 dot, so many sample functions are there. So I am plotting. So this is one sample function. Another sample function could be like this. So this is the temperature profile of another city, this is for one city, this is for another city, and again so on. And let us say, consider this is waveform corresponding to last city. So this is the waveform, which consists of realizations. This is one realization, second realization, and so many realization in between, and last realization. So collection of realization is what we can say is a random process. So as I told you, so you can denote this like this, x, t is varying, and one realization, if I show it by, let us say, h0, small h0, then this is small again this is, if I consider this, yes, so on. If we go like this, you are having, let us say, t, entire t and Sn waveform. So this is one first realization, second realization, in between so many realizations are there. This is the last realization, where n is the sequencing index, right? N is the index subscript. So here ideally that n has to be infinity, so that we get complete picture about the underlying physical phenomenon. If we are really want to study that random process perfectly, in that case n has to be large. Ideal value of n is infinity. Those collection of waveforms or collection of sample function, right, that sample function is called ensemble, and ensemble is nothing but a random process. So in nature there are many physical phenomena, they are taking place, they are occurring, and one of the way to represent these phenomena is represent in terms of statistics. If you use statistics, we can represent those physical phenomena. Most of the phenomenon in the nature, they are random in nature. There are fluctuations, cannot be directly recorded. So what we do is we talk about their statistics, right? Can be modeled by using their statistics. That is what I said. That was the first statement I said. There are various physical phenomena, they are occurring in nature, and those phenomenon can be modeled by their statistics. So in simple way, somebody wants to remember what is random process. So you can say that it is a mapping from S cross R to R. That is enough to define the random process. So suppose if I read the random process at t0, t1, t2 at different instant. Let us say I read it at t0, instant is t0, t1, t2 and t3, instant is t3. I am reading the random process, okay, at the instant t0. I am going with all the waveforms, all n waveforms at the instant t0. I am observing the random process at t0, t1, t2 and so on, and considering all sample functions. In that case, whatever we get, let us denote that by x of t0, x of t1, x of t2 and so on, like this. This x of t0, x of t1, x of t2, this capital X is a random process, right? Random process, what you get here actually? Random process you can denote like this way also. Here, this, what is giving this? Let us say this is giving S, it is giving T, R is giving T, this S is giving S. You can denote by x of st, or you can write like this way also, x of st, or you can write like this also, x of t s. We can write various ways, okay? Whatever we are using, we have to define clearly, right? So here if I read random process at the instant t0, at the instant t1, at the instant t2, at the instant t3, so I am reading all the waveforms, okay? Value of the random process at particular instant is called random variable, right? Random process at particular instant. If I take random sample of the random process at particular instant, so sample is containing so many values, because it is a random variable, and random variable it can take one value out of so many values, and that value which it is going to take, it is decided by outcome of the experiment. So depending on outcome of the experiment, random variable takes the values. So random variable is a mapping from sample space to real line. So random variable, each sample of the random process is a random variable, and which value that random variable is going to take, it is unknown. So here random process is nothing but sequence of random variable, so it is unpredictable. At t1 what is the value, at t2 what is the value, it is random, it is decided by the outcome of the experiment. So we can say that it is what value that random process is going to take in the next instant, it is not predictable. Because random process is nothing but collection of random variables. If you see, it is a collection of random variables. So right, that when I take samples, naturally if t is very very small, in that case it will give closure picture of the random process, and t is sufficiently large, then we get a bigger view of the random process. So what I am saying is, it is collection of random variable, and random variable, what value it is going to take, it is decided by the outcome of the experiment. So because of that, random process, what we say whenever we define random process, we say that what value it is going to take in the next instant, it is not known. So x of t0, x of t1, x of t2, they are the random variables, and collection of random variables, index sequence of random variable, we say it is a random process. Whenever we go for this one, discrete random process, we say we are having sequence of random variables, and that time what we say is index sequence of random variable is called random process. So here x of t0, x of t1, x of t2, they are the t1, t2, t3, they are instances. Suppose if I shift these instances, each of these instant, by some time tau, so what happens? It becomes x of t0 plus tau, x of t1 plus tau, x of t2 plus tau. And if I take again those variables, consider all those variables, they are also random variables. Here I took at t0, t1, t2 at the first instance. Now later on I tried to start my t0 at t0 plus tau, and again I took all those random variables. So here the random process is nothing but collection of random variable. So since there are more than one random variable, so there will be a joint probability density function. For each random variable, it has its own probability density function, and set of random variables, if I am considering, they are having a random probability density function x of t0, joint probability density function x of tn. So x1, x2, so on xn. So this is joint probability density function when the instant was t0, t1 and tn. So joint probability density function when I consider the instant of random variable t0 plus tau, x1 of xt1 plus tau, x of t plus tn plus tau. So what I am doing, I am taking the density function x1, x2, xn. Here some books they write like this, t0 plus tau, so on tn plus tau. Here also I can write, here in this case I can write comma t0, t1, tn. So value taken by the random variable and instant, value taken by the random variable and instant. Here I am shifting the entire time axis by tau, let us say like that, and take the samples similar to t0, t1, t2, tn with the same gap, whatever gap which you use while taking t0, t1, t2, tn. So process is, we can say that process is shifted and I am taking samples, or I can say that I am taking sample at t0 plus tau, t1 plus tau, t2 plus tau. So samples are chosen. So if I say that all this is joint density function, this is also joint density function. If both these joint density functions, they are same for all values of tau, in that case and all order density functions, joint density, first order joint density function, second order joint density function, third order joint density function, means joint density function of 3 random variable, 4 random variable, 5 random variable. If I take all joint density functions, and if I see for joint density function for 4 variable, joint density function for 4 variable, here also after instant of tau, if these joint density functions, they are matching for all tau, then we can say that it is stationary process. Not only stationary, it is strict sense stationary process. Strict sense stationary process. If all order density functions matching, these two, they are matching, okay, for all tau, these density functions, they are matching for all tau, then we can say that the corresponding random process is strict sense stationary random process. Okay, suppose we are having random variable. Another definition I would like to give here. If you are having random variable, and if I take mean of random variable x of t0, which is naturally x random variable and density function of that random variable, okay, dx, we can say like this. So this is mean of random variable at the instant t0. If all means, that is mu x t0, mu x t1, mu x so on, mu x tn, okay, so this is mu x t1. All these means, they are equal. This is one thing. So first order statistics of all random variable is equal, and second order statistics, that is correlation. So correlation r of t0 t1 is expected value of x of t0 into x of t1, random variable at the instant t0. Let us use same notation, okay, so as to have uniformity, there will not be confusion if I use same notation. X of t0 and x of t1, these are the two random variables, and r x t0, r x t1, right, autocorrelation between the random variable t0 and t1, it is equal to r x t0, r x t1, right, which is equal to t1 minus t0, okay. So in that case, what is the meaning of this is the autocorrelation is function of time difference. Autocorrelation function is function of time difference, right. So in this case, what we can say that if 1 and 2 they are satisfied, we say that corresponding random process is wide sense stationary process, wide sense stationary random process. What is that I am saying? Their first order statistics, mean of random variable, all random variable must be same, and second thing is autocorrelation function is function of time difference. Then we can say that process is WSS process. Okay, let us see the picture of discrete random process. If random process is discrete, how it looks, that is what we'll see. So I will again draw picture taking few waveforms. I told you that more number of waveforms, it means more clarity, more information about the underlying process. So something like this. something like this. And so this is, I am representing the process is x of n, and I am saying here it is zeta. So this is random process. This is notation for random process, and that too it is discrete random process. Okay, in this case, if I fix my n, let us say n is n1 and zeta is not fixed. Okay, here that let us consider that first one is x of n0 zeta, second x of n1 zeta, right? So set of zeta on zeta, sorry, the first waveform is x of n zeta 0, second waveform x of n zeta 1, and so on, x of n zeta n. So there are n waveforms. So first waveform is x of n comma zeta 0, n is varying, this is time axis, and okay, it is sample. Instead of s, I am using zeta 0, first sample function, zeta 1 second sample function, zeta n nth sample function. So here, if suppose your function is fixed, let us say instant is varying, n is varying, function is fixed, so we say it is single realization or deterministic function. If I fix n, let us say n1, and if I say zeta, all zeta, okay, this is my first instant n0 n1, so I am fixing this entire, all zetas are coming, so I am fixing all, okay, n1 instant, maybe here all samples coming at n1 instant, x of n comma zeta 0, okay, though it is I am saying here, let us say in between there are some other samples also, we have not taken those things into account. So this is n1 is fixed and zeta is varying, it is random variable, and if I say both are fixed, let us say n2 and let us say zeta 1, both are fixed, so it is n2 is particular instant, let us say n2 here, and zeta 2 is here somewhere here, then zeta n2 and zeta 2, so it is single sample, so single value, okay, and both are varying, it is a random process. Realization is fixed, it is a deterministic function. Time is fixed, it is a random variable. Both are varying, it is random process, and both are fixed, it is deterministic value. So this is all about a random process. So a random process, while this one explaining the random process, I took the example of this one, temperature fluctuations for the different cities around the world, and all these temperature profiles put together one above the other. What we are saying, it is a collection of waveforms, and that is also called as ensemble, which is function of time, and that is a random process as far as that variation in temperature is concerned. So I also told the example of noise across the registers. If we are having electronic device having so many registers, if I measure the noise over the period of time across all the registers and plot their waveforms, that also becomes a random process. I told that random process, to describe the to handle the random process, to interpret the random process, to model the random process, we need to speak about its statistics. We need to represent, or we need to understand those processes in terms of statistics. Directly it is not possible to model those processes, since I told you that random process is nothing but collection of random variables, and random variable at particular instant what value it is going to take, it is decided by the experiment. So the next sample what random process is going to take or random signal is going to take is unpredictable. Okay, and I also told you that simplest way is collection of random variable is called random process. In terms of mapping also I told you that it is a mapping from X cross R to R. That is also very easy to understand, very easy to remember. And in case of discrete domain I took the example collection of waveforms. Along x-axis there is a time instant, along y-axis there are realization or outcomes of the experiment, function. Okay, these are the outcomes of experiment. Amplitudes are nothing but outcomes of the experiment. If I say x n comma zeta, it is a random process. If I fix n, it becomes random variable. If I keep n as it is, fix zeta, it becomes single realization or it is called deterministic function. And if I fix n as well as zeta, it becomes single value. So we can consider same thing as a different entity by changing the notation, right? So n0 is fixed, so it means random variable is there. Zeta is fixed, it means realization is there. Both are fixed, it means single sample. And nothing is fixed, both are varying, it means it is a random process. Right? Why we should study random process? Because there are so many phenomena in the nature, they are random in nature. It is not possible to model those phenomenon or model those processes indirectly. So we need to take the help of statistics to model such phenomenon. So that is why we need to understand this concept while doing the research, because many times in research we assume that random process is nothing but single realization. In that case what we are assuming is that it is a ergodic process. In case of ergodic process we use single realization to describe the entire random process, and this is only possible when the process is stationary, right? And time average and ensemble average. Time average is horizontal average and ensemble average is vertical average. Both should match. In that case we can say that process is ergodic. And in case of ergodic process, what happens? Single realization of the process has so many realization, but one function of the process is sufficient to entirely describe the process. But in case of non-stationary random process it is not possible. So whenever you are doing experiment, please see that what kind of process you are having, whether you are having stationary process or you are having non-stationary process. In case of non-stationary process you need all realizations, but in case of stationary process you can use single realization to represent the entire process. And many times if it is non-stationary, what we do, we take segment wise and we assume each segment is stationary and we find the statistics. That is also possible while carrying out the research. Okay, thank you. This is something about the random process which I wanted to tell you.